We're going to continue on here. Chapter 10, we got into, which was about energy. And so remember, energy is really sort of the flow of heat or energy. And as we talked about, heat does flow from hot to cold. So again, the hot sort of object will transfer that energy to the cold object. The result of that is we will see the temperature start to increase in the colder object, obviously start to decrease in the warmer object. We really talked about last time sort of two types of processes involving energy. One is an exothermic process where heat and energy is released. The other type of process that we talked about is an endothermic process. And in an endothermic process, heat and energy is absorbed. And we talked about some examples of this, but again, a very common example of both of these type of processes are, for example, phase changes. So when we go from, say, solid to liquid to gas, that process of going from solid to liquid to gas all involves energy being put in. The result of that is everybody gains a little bit more energy, and eventually they get to the gas phase where they're flying around free from one another with a lot of energy, and those are all endothermic processes that occur. So if you just take a simple thing like the ice cube, when it comes out, it is going to absorb all that energy from the air and start to melt. If you take liquid water and want to make some pasta like we talked about last time, put a little fire underneath that, it's going to pick up all that energy from the fire, and that's going to cause it to go from the liquid state to the gas state. Going opposite, if you go from the gas state to the liquid to solid as they're flying around and they release energy, they no longer have enough energy as they come in contact with each other to sort of escape one another, and they sort of cling to each other and fall out of sort of the gas phase into the liquid phase. Thank you. And they will continue to do so if you continue to remove that energy. They will no longer have enough energy to really to pass one another, which is what we see with liquids, which is why they're fluid, and then they'll sort of lock into place into sort of the solid state. So exothermic, endothermic are really important sort of processes that occur in chemistry. The way that we oftentimes can sort of see these, as we talked a little bit about last time, and we'll talk about again here today, is what's known as the change in enthalpy. And the change in enthalpy is basically the energy either gained or released sort of in a reaction. The delta symbol here means change. And how sort of in general, when you calculate energy sort of calculations in chemistry, you can sort of determine if something is exothermic or endothermic. It's actually by the sign of it. So typically speaking, when you calculate things that are exothermic, you usually will end up with a negative value, excuse me, for the energy. And when you do anything that is endothermic, typically you will end up with a positive value for energy when you do so. It is really based on what we see in relationship to somebody either gaining or losing energy, and that's temperature. And when we do something like the change in temperature, that is the final temperature minus the initial temperature. So if somebody gains energy in an endothermic process, their final temperature in terms of endothermic, their final temperature will be a larger number than their initial, which would be a smaller, and we'll end up really with more of a positive change, which will actually keep our energy value positive when it's all said and done. And if it's an exothermic process, when we look at temperature, we will actually see the temperature start to decrease as it loses all that energy. The temperature of that substance will come down because it's no longer moving around really fast, and creating that sort of high temperature will actually have a smaller number minus a larger number, and we'll end up with more of a negative number overall for energy when it's all said and done. So temperature oftentimes is really the key in determining sort of what's happening in terms of the process. And it's a really simple thing you could do. It's just a thermometer, stick it in something and just follow what's happening with the temperature. And you could sort of understand just by looking at that in a lot of cases, are you dealing with an endothermic or exothermic process? We talked about reactions just in general because it is chapter 6, so they kind of assume you did the other chapters, which we didn't yet. But again, when we talk about chemical equations or reactions, we start with reactants and we end with products. And again, the reactants are really our starting material, and the products are really what is formed as a result of the reaction. So a lot of times when we talk about thermodynamics, which is involving this energy, a lot of times what we look at when we talked about, for example, with state functions, the only two important things is sort of where you begin and where you end. And in a chemical reaction, sort of this is our final state where our products are, and our kind of initial state where our reactants are. So a lot of ways that we can calculate energy, as we'll talk about a little bit today as well, is actually doing that, taking the difference between sort of where the products end up in energy and the reactant started, and that will again tell you if it's endothermic or exothermic. Any questions on any of that stuff we talked about last time? Okay, so let's continue on here and talk about a few things. So speaking of this sort of idea of exothermic and endothermic, as we've been talking about, we can also display these in these type of pictures here. These are what are referred to as energy diagrams. And we have two different types of energy diagrams up here. The one on the left is an exothermic reaction. The one on the right is an endothermic reaction. And as I mentioned a second ago, we have our reactants in this case basically going to our products. So when we look at an energy diagram such as this, two important things to really sort of find and isolate where they're at is where the reactants start. So I'll just put a big R right there in terms of energy versus where the products are in terms of energy. And in the case of a exothermic reaction like we see here on the left-hand side, our reactants are much higher in energy to start with than our products. So whenever you have our reactants higher in energy than our products, typically what that means is this is going to be an exothermic reaction. The only way that our reactants can get down to our products in terms of energy is overall energy has to be released here in this reaction, which is an exothermic sort of process. So what happens in a chemical reaction? In a chemical reaction, really the only thing that's happening is you're making bonds and you're breaking bonds. You pretty much break all the bonds on the reactant side, and then you make new bonds on the product side, which gives you new substances that are formed, which is what a chemical reaction is. It's a chemical change. Something new has been formed on the product side. So really in a reaction, that's what happens. We break some bonds and we make some new bonds and make some new sort of substances on the other side. Now, does every sort of collision that occurs, which is one of the things that you need for a reaction to take place, result in products being formed? The answer is actually no. You basically need everybody to collide with one another to start the process of a chemical reaction, but they actually do need to sort of collide with each other in the right spot. So they actually have to hit each other in the right spot, sometimes called the active spot, for that reaction to occur. The other really major thing that has to happen in order for a reaction to occur is they have to actually hit each other with the right amount of energy. So just because two things sort of collide on the reactant side, it doesn't necessarily mean that products will be formed. They need to hit each other in the right spot and also have the right amount of energy. What is that right amount of energy? What happens as this reaction takes place is the reactants are starting to climb this kind of hill, and eventually they'll reach kind of the top of the hill here. And the top of the hill in terms of energy is what is referred to as the transition state. That is pretty much your highest point in energy along the way in this chemical reaction. And the amount of energy required to get up that hill for your reactants, that is what is known as the activation energy. So the activation energy is the minimum amount of energy needed for a chemical reaction to take place. It is, if you want to think about it, really the hill that those reactions has to climb in terms of energy to get to the other side. So when they get to this very top of the hill here, which is the transition state, that they actually make something up here, and I'll just make it a little bluish here. This is what is sometimes referred to as the transition state complex. Some people call it the activated complex. And what that thing is essentially an intermediate between the reactants and the products. And as these guys are climbing up this hill, coming to this top of the hill, what you actually have happening is you have all those bonds that you need to break starting to break. So you got partially broken bonds happening. And then you actually have partially made bonds as well. So they're starting to make some bonds and break bonds at the same time. You get to the peak of energy here where you have this transition state complex, which is something that has kind of partially made bonds and partially broken bonds. One thing that you should know in terms of energy and chemistry is things that are in really high states of energy is not a really stable situation. Pretty much most things in chemistry are done to lower the overall energy to come to a more stable state. So things in lowest energy possible is really the ideal situation for things in chemistry. When we have things in really high energy states, they're not very stable. And you can imagine if you have something that has some bonds that are sort of broken and you got some bonds that are actually sort of made, that's something that's very transitional and it's not a very stable type of thing. So that's why we see it very high in energy here on our diagram. And typically speaking, that transition state complex will kind of drop down to the other side relatively quickly at that point and make your products that happens in that type of reaction. If we look on the right-hand side, this is for an endothermic reaction. If we locate our reactants versus our products, our reactants are down here in energy, and our products are actually up here in terms of energy. And we have kind of the opposite situation in this case. Our reactants are actually lower in energy than where our products are. And the only way for our reactants actually to get up there in terms of energy is energy needs to come in. So energy needs to be absorbed. And this is why this is a endothermic type process. So whenever you see an energy diagram where you have reactants lower in energy than your products, that is an endothermic reaction. Heat and energy does need to be absorbed in this particular case. So do we have an activation energy here? We do. This guy's going to start climbing this hill, making bonds, breaking bonds, partially broken. It's going to get up there to our transition state over here, just like on the other side, where we have that transition state complex that's going to kind of fall down to the other side relatively quick. In this case, our activation energy is actually all that right there from our reactants to the peak of the hill. And the activation energy, by the way, is sometimes abbreviated E of A, is the activation energy, is what it is sometimes abbreviated as. This hill that the reactants have to climb to get to the other side also plays a really big role in how fast or slow a reaction will take place. So if you just visually look at it, we can kind of see just from these two diagrams here that our endothermic one actually has a much larger hill than our exothermic, and that's maybe why it's an endothermic reaction. Got to throw a little extra energy in there to help everybody up and over that big hill to kind of get to the other side. So these activation energies play a really important role in terms of how fast or slow a reaction takes place. If you have a really big activation energy, you're probably going to have not as much reactants that have enough energy to get up and over that hill to the other side. The result of that usually means you'll have a much slower reaction. If you have a lower activation energy, you probably have a greater number of reactants, molecules that have enough energy to get up and over to the other side. If you just think about it, for example, if you're walking in the parking lot over like a speed bump, it's a small little hill. you should have no problem, right, getting up to the other side. If you go in the parking lot to the hill on the other side of the parking lot over here, right, and you want to get up to the other side, it's going to take a lot more energy, right, to get up and over to the other side. Maybe there's some people that can't get up and over to that other side, right? So there's not going to be the same proportion of people, for example, that could just go over a very small speed bump to get to the other side. So activation energy really does play a pretty big role in, whether or not or how fast a reaction will take place, which is sometimes referred to as the rate of a reaction, which you actually talk about more in kinetics in 1B. Now, a couple of other important things. As I mentioned earlier, when we talk about energy, really the change in enthalpy, that delta H of the reaction, is really the sort of value that we oftentimes look at to determine whether or not a reaction is exothermic or endothermic. It's not, again, really the number that's all important. It's really the sign. Is it positive or negative? That's really the important determining factor as to whether or not a reaction is exothermic or endothermic. One way that we calculate the delta H, for example, of a reaction is we take the delta H of all of our products and we subtract it from the delta H of all of our reactants, right? And when we think about, again, our products, that's our final state minus our initial state, basically, is what we're doing. So we're taking basically initial and our final states and determining what's going to happen. So if we just look at this for our exothermic, our reactants are up here, our products are over here in terms of energy. If we take the difference between the energy of those two, that will give us our change in enthalpy. So if we were just to put this in here for our exothermic reaction, what we see is our products are lower in energy, which means it's going to be a smaller number, minus our reactants, which is a higher number, which is going to be a larger number, and that's going to result in a negative value for delta H. So if you take a smaller number minus a larger number, you're going to end up with a negative number, and that will give you a delta H for an exothermic reaction. It's going to be negative. If we do the same thing over here for our endothermic, taking where our reactants are starting versus our products, take the difference here, that's our delta H of our reaction. And if we do it for that guy, the delta H of our reaction, which is our products, which is higher in energy, so that's going to be a larger number, minus our reactants, that's a smaller number. So a larger number minus a smaller number will result in a positive value for an endothermic reaction. So once again, that is probably, I would say, in chemistry, 9 times out of 10, how you would determine, for example, if you're given some information in a problem, whether or not this thing is an exothermic or endothermic process is really by the delta H value that's oftentimes given to you. And again, the number doesn't matter, but that sign is really important. Also, as we'll talk about as we go through this chapter, why it's really important when you do calculations, for example, involving temperature, which is ultimately a lot of times what determines whether or not you get a positive or negative number, that you always do final minus initial, so that if you do have a negative, you end up with a negative and your energy becomes negative. Or if you have a positive, you end up with a positive value for energy. Any questions on that there? Now, one way, speaking of sort of why we have these here, one way that we can, for example, speed up a chemical reaction, typically speaking, is to add a catalyst. And a catalyst is something that is typically added. It is not a reactant. It's not a product. And it does not get used up in a chemical reaction. It is usually there solely, for most cases, there are negative catalysts, but most time when people talk about catalysts, they are there to speed up a chemical reaction. How do they do that? Well, one simple sort of idea of how they do that is, let's just say, for example, you have 2 gas molecules that are flying around. If they're flying around by themselves without a catalyst, they got to wait for themselves to find one another, right? Be in the same vicinity, and they're moving around pretty fast. So maybe that doesn't occur very fast, right? So it takes a while for them to sort of find one another so that they can bang into each other and react. Now, if you add something like a catalyst, say like a metal catalyst, for example, just a piece of metal that each of these gas molecules are maybe attracted to, what that then does is put them both pretty close to one another in the same vicinity pretty quickly, and that's going to allow them to interact with each other a lot quicker. The result of that is you're going to actually see a lot faster of a reaction occur. So a lot of times catalysts are added to a chemical reaction to speed up a reaction. You can usually see catalysts in a chemical equation. They are usually written, for example, on top of the arrow. So you may see something like PT, which is platinum, as a common catalyst. You may see something like H+, which is an acid that's written on top of the arrow, and that's used as a catalyst. So sometimes you'll see catalysts sort of written on top of the arrow, and they are able to find, I guess a lack of a better description is a better alternative pathway for that reaction to take place, a more efficient way for that to occur. The ultimate result of that when we look at our energy diagrams is if you added a catalyst to a reaction, what you will typically see is you will typically see the activation energy lower. So instead of having to climb the top hill, you will have a much smaller hill for them to climb. The result of that is, if that little blue line there is my catalyst, the result of that is there will be a greater number of reactant molecules that will actually have enough energy to get up and over to the other side. Because there's more molecules can now get to the other side, you basically are able to see the reaction occur a lot faster and it speeds up. So by finding that sort of alternative pathway, it lowers the activation energy and allows more sort of reactive molecules to be able to make it to the other side. If we went back to sort of our example of the big hill in the parking lot, if by some way somebody could just lower the hill down, right, again, that's going to allow a lot more people to get to the other side of it a lot easier. Or the old cartoon where the roadrunner just opens the trap door and goes through the mountain to the other side, right? And the coyote hits the mountain straight on. Any questions on that there? All right, so here again is just another form of an energy diagram here. These are our reactants here, the formation of water, and our products. And overall, we see our reactants higher in energy than our products. Energy, again, needs to be given off in this case to allow those reactants to come down to the products in terms of energy. Here, this is our reactants down here, our starting material, and this is our products. Again, in order for our reactants to get up there in terms of energy to our products, heat and energy overall needs to be basically put into the system to allow that to occur. And that's basically a decomposition of mercury 2 oxide into mercury and oxygen. So a couple of other thoughts here on exothermic and endothermic, and maybe some ways that you may sort of see it in an equation. Sometimes, and I would say very rarely probably here in the classes you'll take, will they actually put an energy value into the equations, but sometimes they might. So that's what we see here. We see 213 kilocalories, a reminder that a joule and a kilojoule are very common units of energy, and also a calorie and a kilocalorie are also units of energy. And while we're at it, right, 1 calorie is 4.184 joules. And again, that's a conversion we talked about that you do need to know. And that's a conversion between joules and calories in terms of units. So in this particular case, what we actually see written into the equation is on the product side, we see energy, 213 kilocalories written into the equation. And that would signal that it is a exothermic reaction. So if you happen to see in an actual equation an energy value written on the product side, that would be like it's being given off or released to the product side in this reaction. And we think of energy as a product. Opposite is true if we had another reaction here where maybe we have some energy here on the reactant side. That would signify that this reaction is an endothermic process. Basically, it's like it's being absorbed by the reactants for this reaction to take place. So I would say, again, in most cases, you probably won't see too much of energy written into the equation. More so for us in chemistry, as you go through your classes here, you probably won't actually see a value written in the actual equation. You will probably see more of that delta H number written next to it. And again, if you see that that value is a negative number, that will automatically tell you that that's an exothermic reaction. And same thing here, you'll probably see like a delta H. Again, it will actually give you the number, but obviously the number is not all that important in terms of exothermic or endothermic in this process. That is probably most likely how you would sort of see it. We will also see this towards the very end of the school year here in the very last chapter when we talk about equilibrium and Le Chatelier's principle. And the idea in Le Chatelier's principle, as we'll talk about then, is this idea, we think of exothermic as being sort of a product in terms of energy, and we think of energy being a reactant in an endothermic reaction. Not really correct in all aspects, but in that sort of application, as we will see, we kind of think of it that way. So as we've been talking about, again, heat's going to flow from hot to cold. So in this case, we will see the heat really flowing from our hotter temperature here, which is our 90 degrees, into our colder temperature. That's going to result, obviously, in warming of our cold water side. In terms of temperature here, we're going to see, obviously, the hot side go down as it's releasing that energy. As the cold side picks up that energy, we will see again an increase in the temperature of the cold side. In an insulated container, they'll probably meet somewhere in the middle there at 50 degrees. 90 plus 10 is 100, divided by 2 is 50, about average between them. Now, enthalpy, which as I just mentioned a second ago, is probably your most common way that we do see energy sort of displayed in chemical reactions. So the change in enthalpy, as I mentioned, is really a fancy way of saying, overall, is this reaction releasing energy? Is it absorbing energy? So it sort of gives you how much energy is either released or absorbed in the process of a chemical reaction. The delta H, which is the change in enthalpy, is the value that we look at. And again, we take our products minus our reactants, which, as we've been mentioning, is essentially our final state minus our initial state. And if that calculation in the end ends up, as we've seen, a positive number, then we know it's endothermic, and a negative number, we know that it is exothermic. So how would we do, say, a calculation like this? Typically speaking, if you're only given the equation and you want to kind of calculate the delta H for a reaction, this is pretty much a table type of situation. You're going to go to the table and you're going to look up the values for the delta H's for all the products. And then you look up the values for the delta H's for all the reactants. Usually in that table, it will usually say delta H of F or delta H of formation. That's what the F stands for, formation. Usually the units are kilojoules per mole. It's usually the units that we see off of that table. If you were to go to a table like this, which you might have to do in a problem along the way, there's a couple of things that you always want to kind of make sure of when you go to a table like that. First off, you do want to make sure that you do find the correct substance you're looking for. Secondly, you want to make sure that it is in the correct state. So if what you're dealing with is a liquid, you want to make sure you look up on the table the value for liquid and not the value, for example, for it in gas or aqueous or solid or stuff like that. So it's really important when you go to these tables that you do look it up in basically its state and you find the right thing. This little knot that's on the top, that usually means standard conditions. And when you go to a table like this, standard conditions usually means 25 degrees Celsius, usually means 1 atmosphere for the pressure. And if you're dealing with any type of concentration, 1 molar for the concentration. These are typically what table values mean, and that little circle means is like ideal conditions, if you will. That's usually what you look up. So how do you do this? You basically take your products minus your reactants. So let's just say, for example, we had this equation here we'll go with 3A plus 2B goes to 4C. And let's just say we had a made-up table here of A, B, and C. And our delta H values here, we'll go with negative 115 kilojoules per mole. We'll go with 64 kilojoules per mole. And we'll go with negative 85 kilojoules per mole. So this would obviously be a table. You would go and look up these values here for these specific things. Now, when we do this, the values that you see here is per mole, which means when you look at a chemical equation, you do have to take the coefficients into account. And these coefficients in the balance equation are what are sometimes referred to as the moles of each of these guys, abbreviated MOL, moles. So we do need to multiply the value that we find in the table by the coefficient in the balance equation, because the value we find in the table is per 1 mole, and if we have 4 of them, we need to multiply it by 4 to get the correct value for how many we have. So if we were going to calculate the delta H for this reaction that I just made up, we would start with our product. So I'm just going to do a little bit of that. On our product side, we have 4 C. So we're going to take 4 times the value of C from the table, which is minus 85 kilojoules per mole. That is pretty much going to take care of all of our products. We only have one product in this case. If we had 2 products, we would then add it to the next product and the next product. Here we're then going to subtract from our reactants. And on our reactant side, we have 3A. So we're going to multiply the value for A by 3. And in this case, negative 115 kilojoules per mole. We're then going to add it to our other reactant, which in this case, we have 2 of the B's. So we'll take 2 times the value of B from the table, which is 64 kilojoules per mole. And that's going to take care of pretty much of all of our reactants. So we're going to take our final, which is our products, minus our reactants, which is our initial. And if we do all that stuff there, 4 times negative 85 minus 3 times negative 115 plus 2 times 64. That's going to give me here on my calculator negative 123 kilojoules. You can write kilojoules per mole if you like. Technically, the moles cancel because that's kind of what all these guys are here. These are moles, actually. They're actually moles. They kind of canceled the coefficients. First off, any question on that calculation? So you basically go to the table, you're going to add up everybody on the product side, take the coefficient into account, and then subtract it from everybody on the reactant side, and it'll give you a number. In this case, the number I got is negative 123. This would tell me this reaction is endothermic or exothermic. Which one is it? It is exothermic, and really the only thing I need to know is negative. That tells me it is exothermic. So this is a very common way that you could calculate the energy of this reaction. Basically what this would tell us in my made up reaction here of A, B, and C, overall this reaction is going to release some energy in an exothermic type process, and negative 123 kilojoules of energy is going to release per mole of sort of A that's going on there. Any questions on that there? All right, why don't you try one here with some real numbers? So why don't you give it a go? Why don't you calculate the delta H for this reaction? And these are obviously values you would find in a table. Yeah. Okay, so let's take a look and see. Again, we're going to do basically our delta H of our reaction. We're basically going to take the delta H of all of our products that we find in the table, minus it from the delta H of our reactants. Again, as we talked about a second ago, we do need to take into consideration the coefficients that we find there in our equation. So we'll start here with our product side. And on the product side, we do have 2 sodium hydroxide. So we got to take 2 times the value of sodium hydroxide minus 470 kilojoules per mole. We do have another product in this case, which is the H2. So we do need to multiply it by 1 times 0 for our H2. And just so you know, typically speaking, for delta H's, anything that is sort of by itself, how it naturally comes. So H2 is how hydrogen naturally comes. Sodium there, for example, is how sodium uncombined comes. Will typically have a value of 0. So those guys typically will have values of zeros when you look them up in the table. This will take care of all of our products, essentially. We will then subtract it. I'll go underneath. From our reactants, we have 2 sodiums. So 2 times our value of sodium from the table, which is 0 as well, plus our other reactant, which is water. So that's going to be 2 times the value of water from our table, negative 286 here kilojoules per mole. Again, going to close that up. That's all of our reactants. So if we do all that there, we got 2 times negative 470 plus 0, basically, minus 0 plus 2 times negative 286, it looks like. I think that's going to give me negative 368 kilojoules here. Once again, this reaction is endothermic or exothermic? It is exothermic, again, because of the negative sign here. That is going to be exothermic. So again, overall, what this is telling us, this reaction overall is going to be releasing some energy from sort of where it started to the surroundings. Question on that calculation there. No. All right, let's try another one here, maybe. All right, so give this one a go. Kind of blow it up a little bit, make it easier to see, hopefully. Same thing, calculate the delta H of this reaction, determine if it's endothermic or exothermic, this reaction. Again, those would be delta H formations that you can find in a table that you can look up. Our delta H of our reaction, going to be our delta H of our products minus the delta H of our reactants. And that's usually the key here. If you're just given the reaction and nothing else, pretty much you need to go hunt down a table if it's not given to you and basically look up these values as we talked about. So we'll start with our product side here. Once again, we do need to take into account our coefficients. So we got 16 COs. So CO's right there. So we're going to take 16 times that value that we got there. We're then going to add it to our other reactant, which is 18 of them, times the value for water there, which is minus 286 kilojoules per mole. That again is going to pretty much take care of all of our products there, right? So we're then going to subtract it from our reactants. We're going to do the same thing. I'm just going to go underneath again since I ran out of room. We got 2 of those guys. We're going to take 2 times the value we got from the table there, 208 kilojoules per mole. And again, we're going to add it to 25 of our oxygens. And again, oxygen, that is normally how it comes. So that's going to be a 0 actually from the table. And again, that's going to take care of pretty much all of our reactants. So if we add all that together there, we're going to go 16 times minus 110 plus 18 times negative 286. We're then going to subtract it from basically 2 times negative 208, I believe. And in this case, negative 6492 kilojoules. Once again here, we do see a negative number, which will tell us that it is exothermic in this particular case. Any questions on how to calculate that? By the way, if you're punching all this in at once, you got to be careful. Yes, I think of how you punch it in. Yes, hopefully I did all right, I hope. So you want to make sure you use parentheses and all that good stuff. So I would open a parentheses, open another parentheses, and go 16 times negative 110. Add it to open another parentheses, 18 times negative 286. Close the parentheses, hit equals, then subtract, open parentheses again, 2 times negative 208. Close some parentheses, and you should get the right answer. So just make sure you are sort of making sure you do some parentheses if you're punching it all in at once. Any questions on how to calculate delta H of a reaction there? No. Okay. All right, then let's talk about another way here that we do look at energy in a reaction, a very common way, and how you're going to do it, I think, this week in lab as well. And this is specific heat and specific heat capacity. This number on the bottom is not negative, it's just from PowerPoint. And by the way, I'll box it as well. These numbers here for liquid water are values that you do need to know. They do pop up a lot, 4.184 joules per gram per degree Celsius. But what is specific heat capacity? Specific is the amount needed to raise by 1 degree Celsius. I think it's time when we're talking about the specific heat of liquid water being 4.184. There's actually a specific heat equation, and I go with Q is equal to ms delta T. I will say sometimes people will use a little bit different of a formula, but we'll go with this one. What is each of these? Q is actually heat or energy. And it has units of either joules or calories. So Q actually in this equation has only one unit. And I say that because it is oftentimes mixed up with another value that is in this equation that has multiple units. M here is actually mass, and mass is in units of grams. S is actually the specific heat capacity, and S has units of either joules per gram per degree Celsius or calories per gram per degree Celsius. So the S here has 3 units associated with it. Q has 1. And I can't tell you how many people mix these up with each other. So make sure you do not mix them up. Joules just one, or Q just 1 unit, and specific heat capacity has all 3 of the units together. So the other thing is the change in temperature, and that's actually going to be in degrees Celsius, which is actually one of the few equations in chemistry that we actually keep the temperature in Celsius and not convert it to Kelvin. So usually it's an automatic Kelvin conversion. Specific heat capacity, we don't do that because our specific heat capacity is in degrees Celsius, so we don't need to do that conversion. If you're taking physics, they convert it to Kelvin, but here in chemistry, we actually leave this one actually in Celsius. What is the change in temperature? Change in temperature is really important when you do it. It is the final temperature minus the initial. And as I mentioned a number of times, that is absolutely really critical. And I say that because sometimes people, when they do the change in temperature, they just simply take the difference of the numbers. And that's not good because when we calculate something like Q, just like delta H, if you calculate Q and you end up with a negative number, or you have delta H that's a negative number, these are things that tell us it's an exothermic process. If you calculate delta H or Q and it is positive, these are things that tell us it's an endothermic process. So why doing the final minus initial is really important? It's because the mass is a positive number. The specific heat capacity is a positive number. So the only way that you could turn your Q into a negative number is through the temperature change. So again, if you have a smaller final temperature than you started with, you will actually end up with a negative value, right? And if you have a larger final temperature than what you started with, you'll end up with a positive value. So it's really important to take final minus initial always when you do change in temperature. It will give you a negative or positive value for Q, which will tell you if it's endothermic or exothermic. And by the way, you can very simply, by the way, figure out the change in enthalpy by actually just figuring out the Q. If you do it at constant pressure, which most cases the pressure in the room doesn't change. So if you do an experiment at constant pressure, you could actually calculate Q, which actually will tell you the enthalpy value, the change in enthalpy for that reaction. How easy is it to do a reaction like this? As you will find out on Wednesday, you pretty much just need some styrofoam cups. A couple of styrofoam cups are really great. and you put like your water or whatever you're doing the reaction in, you put a little lid on it and a thermometer. And basically all you have to do is watch the change in temperature of the water. And by following the change in temperature of the water, you can calculate Q, and you can figure out how much heat was either gained by the water or released by the water. And you could also, if you wanted to, figure out the delta H or enthalpy of that reaction that's happening. You could also do it for a reaction. So for example, if you took like hydrochloric acid, which is aqueous in a solution, and you took like sodium hydroxide, which is aqueous in a solution, and mixed them together, because those guys are aqueous solutions, they're pretty much mainly made up of water. And because of that, you could do this type of calculation using this formula, and you could just follow the change in temperature with a thermometer, and you could actually again figure out the delta H or enthalpy of a reaction by just simply following the temperature change with a thermometer. It's a super easy type of experiment like you'll do on Wednesday, and it's very, very easy to calculate how much energy is either absorbed or released. Any questions on that there? Yeah. Which part? I'm sorry. Yeah, so these are the typical units associated with Q. So when you calculate Q or you have Q given to you, they're either usually in units of joules or calories. When you calculate mass, which is what M represents, it's usually in grams as the unit. Temperature is usually in Celsius. And S, which is the specific heat capacity, usually will have one of these two sets of units, either joules over grams, degrees Celsius, or calories. So these are the typical units that you see for these values there. Yeah. Yeah. No, no, it's just typical units that you find. And by the way, that is what the specific heat capacity definition means when you look at the units of, for example, joules, grams, degrees Celsius. How much energy, like joules, is needed to raise 1 gram of a substance by 1 degree Celsius. So that's why it has all three of those units involved. It's basically the definition of specific heat capacity. I personally roll with S for specific heat capacity. Some people will use C to represent specific heat capacity. You'll sometimes see that. Some books and manuals will also sometimes use SH to represent specific heat capacity. For me personally, I use S to represent specific heat capacity, but you can, and sometimes people will use C to represent it as well. So it's the same thing. So if you kind of see C, it's the same thing as S, but I'll use S in here. But just in case you kind of see those other letters, they represent some of those other things. As I mentioned before, this is the specific heat capacity for liquid water, and that is something that you should know. And here's a table specific heat capacity. And as I mentioned before, that guy right there are the 1 calorie per gram per degree Celsius for liquid water is something you should commit to memory. It's also really important when you're using this equation that you do find the right state. If you look at this, this is liquid water, that is ice, which is still water, that is steam, which is the gas version of water. They are all H2O, but they actually have different specific heat capacities depending if it's ice or steam or liquid water. So you want to make sure you're using the correct value. I would say most times you're going to be using the liquid water, but you might come across a problem. Maybe you're dealing with ice or maybe you're dealing with steam that you would actually want to use obviously more closer to 2 rather than 4. So those would be provided for you. As we also talked about, the higher the specific heat capacity, the more energy you need to put in there to see it just one temperature change, degree temperature change in that particular substance. So things with low specific heat capacity, it doesn't take a lot of energy to see a big change in temperature. That is also why I think we talked about last time the bathtub versus the cup of coffee, right? The bathtub has more thermal energy because it has more molecules, but it has a much lower temperature than the cup of coffee. I think it was 40 degrees versus 70 degrees that we looked at in that example last time. And that's because when you have all that water, it's going to take a lot more energy to see the temperature tick up a little bit, right? You can obviously heat up a cup of coffee because there's not as much volume or mass of water in there. It's going to take less energy, and you're going to see a bigger change in temperature with that cup of coffee because just the mass of water that's there is much less than it is in the bathtub. So even though you may be applying the same amount of heat, it's going to take a lot longer to heat up that bathtub to the same temperature that you see in the coffee cup. I think we used the example of like a big pot of boiling water for like pasta versus a pot that has just a little bit of water in it, right? It's going to start to heat up a lot quicker than all that much water is present. All right, so let's try one here. So once you calculate here, what is the amount of energy our heat that's required to raise 10 grams of aluminum. That's specific heat capacity of 0.89 joules per gram per degree Celsius from 25 to 58 degrees Celsius. Let's go with joules. Okay, so let's take a look. So obviously here we're dealing with specific heat, so you should automatically roll into our equation here. Q equals ms delta T. Again, if we kind of pull out the information, we'll see what we got. We're looking for the amount of heat or energy. Remember, Q is heat or energy. And again, that's the one that has the 1 unit associated with it. 10 grams is obviously a mass. We have the specific heat capacity given to us, 0.89 joules per gram per degree Celsius. Again, this is the one with the 3 units associated with it. We have an initial temperature here of 25 degrees Celsius, and we have a final temperature here of 58 degrees Celsius. So we really, if we look at our equation, pretty much have everything we need here on the right-hand side. So we just need to plug it in, and our Q will equal 10 grams times our specific heat capacity there. Again, we want to go final temperature minus initial temperature, so 58 degrees Celsius minus our 25 degrees Celsius. And in this case, the grams will cancel, the degrees Celsius will cancel, and that's going to leave us joules, which is one of the answers we're looking for. So 10 times 0.89 times a 58 minus a 25. That's going to get us 293.7 joules. If we think significant figures here, which we probably should, this number here has 3 significant figures. This guy's got 2 significant figures. And really, when we subtract this to the whole number, we get something like 33, which is also 2 significant figures here. That means really our answer should end up over here at 2 significant figures. And that would get us something maybe like a 290 joules in this particular case. First off, any question on that part of the calculation? We also want to convert it into calories. So that is where you need to know, right? 1 calorie is 4.184 joules. So I'm just going to use the rounded number at this point since I have it. And we're going to take 4.184 joules on the bottom, 1 calorie on top. The joules will cancel, so we'll go with a 290 divided by 4.184. I think you'll end up with about 69 calories. If you didn't use the rounded number, you'll end up with 70 calories in that ballpark, I think. Either one's fine, I think, if you rounded or didn't round in this particular case. Any questions on any of that? Exothermic or endothermic, this reaction? It is endothermic, right? We have a positive value here for our energy. And we see that when we look at the temperature, right? The temperature went from 25 degrees. It gained all that energy. Temperature then went up, right, to a higher temperature. So we see that reflected in the temperature here, that this guy gained that energy, again, reflected with the temperature measurement. Any questions on that one there? Yeah. You don't, unless they ask for it. In this case, the question really didn't ask for it, so you don't need to write it. Other questions? Okay. Let's try another one here. See? So we have 294 joules of heat is transferred to 10 grams of silver. That's at 25 degrees Celsius. What would be the final temperature of the silver if the specific heat capacity is 0.24 joules per gram per degree Celsius? Take a few minutes there, see what you come. Okay, so let's take a look, see how you're doing. Once again, obviously we're dealing with specific heat capacity, so we'll roll with our equation here. We'll pull out the information. So again, with 1 unit there of energy, that is our Q. So again, you don't want to confuse Q and S, which is a very common error a lot of people will make. So that's 294 joules. We obviously have a mass here that's 10 grams. We have an initial temperature of 25 degrees Celsius. We're actually looking for a final temperature in this case, and we do have our specific heat capacity of 0.24 joules per gram per degree Celsius. So we pretty much got this, this, and this. The one thing we don't have is a change in temperature. So that's what I'm going to solve for first, is actually a change in temperature. To do that, I'm going to take M and S and divide it to the other side. That will give me the change in temperature is equal to Q divided by MS. Putting in our numbers here, 294 joules divided by our mass, which is 10 grams, divided by our specific heat capacity, 0.24 joules per gram per degree Celsius. Here, the joules will cancel. The grams will cancel. The degrees Celsius will come to the top when we divide and become just degrees Celsius. And if you do all that good stuff there, about 122.5 degrees Celsius. First off, any questions up to there? A reminder that this is not the answer we're looking for. This is the change in temperature. This is not the final temperature. So we do need to still find the final temperature here. I personally, because I'm going to continue on and do some calculations here, I'm not going to round at this point. I'm going to come back and clean it up at the end. Remember that the change in temperature is our final temperature minus our initial temperature. That means that our final temperature would equal the change in temperature plus the initial temperature as we bring this to the other side and add it basically to the other side. And when we do that, that's going to give us 122.5. Again, I'm not going to round at this point, plus my 25. So again, you want to make sure that you do final minus initial, so you're adding when you should and subtracting when you should, and you don't do the wrong math. If you do that, that's going to get you a buck 47.5 degrees Celsius. Now, we really want to kind of think about where we should end up. So we do need to go back to our original calculation there. And since we're dividing and multiplying here, we're looking at sig figs. That is 3 sig figs. That is 3 sig figs. That is 2 significant figures. That means, technically speaking, this guy right here should have, if that was the end of the calculation, should have rounded to 120 degrees Celsius, right? Which would have been 2 significant figures. We then would have technically took this number, which is a whole number, and added it to this number, which is a whole number. And that means when we're adding, we're looking at decimal places. And that means that we should actually end up at a whole number of like 148 degrees Celsius. Yeah. Obviously, if you use the rounded number here of 120 plus the 25, you'll end up at 145 degrees Celsius, which is about 3 degrees difference. So again, in this case, I probably, again, would not round to the end, but you do need to kind of go back and clean everything up. If you rounded at the end, if you rounded earlier, I think I'd probably still give you the points. But you can see it is, in this case, a relatively large difference between those two, 145 versus 148, in terms of maybe 148 is probably where you should be versus the rounding of 145. So again, that's why we kind of want to wait to the end before we do any type of rounding. Any questions on that there? So let's talk about another very common thing that occurs with specific heat, and it's pretty much like you're going to do on Wednesday in the experiment, which is this. We have energy really transferring from one object to the next. It will transfer from the hotter object to the colder object. So let's just say, for example, we took a piece of metal, and we have this piece of metal. Let's just say it's 110 grams of metal. And let's just say initially we took this metal and we heated the heck out of it to 95 degrees Celsius. So we heated this thing up to 95 degrees Celsius. Let's just say we have another container over here of some water. Now let's just say we have 125 grams of water. And let's just say the initial temperature here of our water was, we'll go with 26 degrees Celsius. Now, if I take this really hot piece of metal and I take it and I throw it into the water here, what is going to happen in terms of the energy here? Will the heat transfer from the metal to the water, or will the heat transfer from the water to the metal in this case? Which way will the heat go? It's going to go from the metal to the water. because the metal is hotter, it's 95 degrees, versus our water that's 26 degrees, right? So our heat flow here for our metal is actually going to flow into it. So for the metal, it is actually exothermic, right? It's exothermic, it's going to release that energy. For the water, it's actually endothermic here. The idea of this is we're not going to lose any heat or energy anywhere. We're going to have a nice, complete transfer of energy from the hot piece of metal to our water in this case. Now, when that water has that metal in it, let's just say that the final temperature of our water ended up at 29 degrees Celsius, right? It gained temperature, right? It went higher because it's gaining energy, right? What I will also know is that piece of metal is now sitting in that water that's 29 degrees Celsius. What will be the final temperature of the metal in this case? If it's the metal is now sitting in water that's 29 degrees Celsius, once it's kind of stops moving its temperature, what should the metal be? It would actually be the exact same temperature as the water. It's going to come to equilibrate with the water temperature, right? So if you put something in some room temperature water, it's going to eventually come to the same temperature, right? They're going to kind of equilibrate to whatever the temperature is of the water as it sits in there. So what happens in this situation is the metal will continue to lose all that heat. The water will pick up all that heat. The water's temperature will go up. The metal's temperature will go down, and it will eventually, because it's still sitting in there, you're not going to take it out, it's going to eventually reach the same temperature as the water. So we know the final temperature of the metal in this case will actually be 29 degrees, the same as the water. And at this point, we actually know enough information. For example, if we wanted to know what is the specific heat capacity of the metal, which is S in our equation. So we actually have enough information. That is because we are following the temperature change here of our water, and we know the specific heat capacity of liquid water is our favorite number, 4.184 joules per gram per degree Celsius. So we know that piece of information. So if we think about water and the specific heat equation for water, which is ms delta T, we have absolutely everything that we need to figure out, in this case, how much energy that water is going to basically absorb, right? So let's do that. Let's figure out how much energy the water absorbed in this case by putting in our numbers. So we'll do 125 grams. We'll use our specific heat capacity of liquid water, which again is a number you'll be seeing a lot. We want to go final temperature minus initial temperature for the water. So our water ended at 29 degrees Celsius and started at 26 degrees Celsius. That is going to give us here 125 times 4.184 times 29 minus 26. And you know what, I'm just going to add here some decimals just to not cheat out my significant figures too much here. So I'm just going to kind of cheat a little bit here and add some decimals to my temperature readings here. So we're going to go zeros and zeros there. I'm just going to add some zeros. So it's going to be 29.0 and 26.0. All right, so we'll do that. And that's going to give me here 1,569 joules of energy. And the grams will cancel, the degrees Celsius will cancel, and we'll have joules that's left over. That number represents how much energy the water gained from the metal, that hot piece of metal that went in there. Now, how does that help us with the metal? So we talked about the idea of energy being transferred kind of perfectly, if you will. So if the water gained all that energy, the only place it got that energy from was the piece of metal that's in the water, right? So the metal had to lose the exact same amount of energy, except for the metal, it is exothermic, as we've been talking about. So there's this relationship that Q of the water will equal negative Q of the metal, or however you want to do it. You got to have a negative somewhere. So if our water lost 1569, then the Q of the metal in this case would be negative 1569 joules. Our water gained 1569 joules of energy. The metal lost 1569 joules of energy. Exact same number. The only difference is the sign is different. So that's an important relationship. Actually, Q of the metal is what most people do, minus Q of the water, I think, is what most people do. We'll go that way with it. It's the same result. So in this case, we can very simply, by using actually coffee cups like you're going to do on Wednesday, you can basically just follow the temperature of the water and figure out how much energy the water gained, and you can relate to the knowing now that's how much energy my metal just lost and released. Any questions on that there? That's helpful because now if we do the exact same equation for the metal, which is our Q is equal to ms delta T, we now have Q of the metal, we have the mass of the metal, and we have the change in temperature of the metal. That's going to allow us to solve for the specific heat capacity of the metal. S would equal Q of the metal divided by m delta T. We're basically going to take that and divide it, and take this guy as well and divide it to the other side, essentially. Putting in our numbers here, our Q is going to be negative 1569 joules. Our mass of the metal is going to be 110 grams. And our final temperature of the metal is 29 degrees in this case, minus our initial, which is 95 degrees in this case. That's important because when I take 29 minus 95, what type of number do I get, positive or negative? I can get a negative here. That's going to turn this negative into a positive number that you need for your specific heat capacity. It has to be a positive number. So if we do that here, see how bad I did making up numbers? Not too bad, I think. I did probably pretty bad, actually. No, I hit the wrong number. 1725.9 divided by 29 minus 95. Try that there. No, I did pretty bad here. So we got... There we go. That's better. We end up with 0.2037. The units here do not cancel, so none of these units cancel. I'm just going to write the units underneath, joules per gram per degree Celsius in this particular case. So let me just make sure I punched it in right here. Okay. Now we do need to... I did not punch it in right. Let's go with 0.216115. We'll call it. That's better, I think. All right. Now we got the right number there. We got to think about sig figs to finish out here on. So going back to our original calculation here of the water, this has 3 significant figures. That has 4 significant figures. And when we take, obviously, our 29 minus our 26 with the decimal I put in there is 3.0. That is 2 significant figures. Technically speaking, this number here that I did not round should actually end there at 2 significant figures. That means I'm taking 2 significant figures divided by 2 significant figures. And here we have a lot more than 2 significant figures. We've got 3 significant figures. So really, we should actually end up at 2 significant figures from either of these things. And we'll end up at 0.22 joules per gram per degree Celsius. So this is a very common way, and you'll do it on Wednesday as well, that you can just simply follow the change in temperature of water and figure out based on the water, because you know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. You could back relate it to how much energy was lost by the metal. Any questions on that there?